coefficients. Before we proceed, how many properties have we seen? 7 according to my notes. It's a good idea to denote this as an 8th property, but it was in fact a solution that should be necessary in the solution of a problem that we will have now, and that is this. What happens to the Fourier series coefficient of a signal which corresponds to the derivative of another signal? In other words, if x of t corresponds to Fourier series coefficients of ak, what can we say about the time derivative signals? Let's call it y of t, Fourier series coefficients. What are bk's in terms of ak's, in other words? How can we do that? I can give you the answer immediately, but it's quite easy. All you need to do is you have to write down the Fourier series coefficient representation of x of t, which was something like this. For all k from minus infinity to infinity, ak e to the jk omega 0 t, as we all know, for a periodic sequence of x of t. When you take the time derivative of this, what comes out of this expression is nothing but this thing coming to the side of ak. So you will have ak times jk omega 0 times e to the jk omega 0 t. And over here we immediately see that this is y of t, therefore this portion corresponds to bk. And we conclude that the relation between bk and ak is bk is equal to jk omega 0 times ak. So everything, all the coefficients are multiplied by a jk omega 0 when you take the derivative, the time derivative. Now this is an interesting thing, and the similar property exists for Fourier transform, which will be formulated for not necessarily periodic signals. For general signals we will have a Fourier transform, and over there this thing, so-called k times omega 0, will correspond to omega, the frequency itself. That is the frequency of the coefficient, the kth coefficient, the kth harmonic. So you multiply with the frequency, j times frequency, when you take the derivative. And it automatically vanishes or annihilates this ak coefficient when k is equal to 0. All right? When k is equal to 0, you multiply by k times omega, and since k in the derivative form, and since k is equal to 0, you multiply by 0. For many regular cases, when ak is a finite value, and it must be a finite value, when a0, in other words, is finite, you multiply it by 0, and you necessarily make a0 to be equal to 0 when you take the derivative. And that makes sense, because for a normal signal, let's consider a sinusoid with some bias, something like this. When you take the derivative of this thing, the DC coefficient goes away. So from a derivative signal, you don't really have a DC coefficient. You never have it. You get rid of the DC. And because of this, A0 or B0, in fact, becomes 0 times something which is 0. That's why you don't have a DC coefficient after taking the derivative. And this formulation also agrees with that. So that is the formula. The inverse operation of this thing is the integration. That is, if what would happen if y of t is equal to from minus infinity to t x of tau d tau, that is the accumulation of x up to the point of t, then we just need to invert this formulation using the same logic, and we say that bk is equal to 1 over jk omega 0 times ak, except of course k is not equal to 0, because that k is equal to 0 will correspond to the DC component, and we don't know that. That must be handled separately. It's like you know, in improper integrals we have a plus c. We have an expression plus c. That plus c is the DC thing of the formulation, and that plus c DC must be handled or evaluated separately. So we don't consider that in this formulation, and as a matter of fact it's a dangerous formula. As you see, k is in the denominator, and when k is equal to 0 we have a problem. In fact, consider again the same x of t. What would happen to the DC coefficient of the integral? As you see, from minus infinity up to a certain point, since there is some certain amount of DC, that DC will be accumulated, and the value of A0, the DC value that we get, would diverge. In fact, the integral of this thing will not even be periodic. It will be just growing to infinity, blowing. So the only thing that we can integrate, the only types of signals that we can integrate in this formula are the signals with 0 DC. If DC is 0, then A0 will be 0, and this will be a 0 over 1 times 0 over 0. That will be an ambiguity, and you have to use then the Hospital's rule to find out what really that thing may correspond to. We will consider therefore only such 0 DC signals for the integrals. Now we will use these two formulas, but except for the DC coefficient, let's forget about that. You can just evaluate the DC coefficient A0 or B0 separately. Don't take that formula from these equations. For the derivative, this is the formula, and for the integral, this is the formula that we use, except for k is equal to 0 case. Now let's use it. Previously, the last example that we have seen was this signal. If you remember, something like that. It's a periodic sequence generated from an x of t. So we called this thing y of t, and we in fact generated this y of t from this x of t. We called this thing x of t, and we said that y of t is equal to x of, this is, by the way, 2, this is 1, this is 2, and this peak value is 1. These peak values are 1 over 2 and minus 1 over 2. And we said that y of t is equal to x of t minus 1, this thing shifted to the right by 1. And then we subtract 1/2 from it, and we said that the Fourier series coefficients of this y, we call it bk, the top sequence or signal, is equal to ak times e to the minus jk pi over 2. When you substitute the period equals 4, omega 0 will become 2 pi over 4, which is pi over 2. And t0, the amount of shift, is equal to 1 from here. Therefore, we have e to the minus j k times omega 0, which is pi over 2, times 1. And this is the formula that we get, except, of course, k different than 0. And over here, we said that then bk is equal to 2 folds. When k is equal to 0, first of all, the DC coefficient of this signal is clearly 0 because the positive and negatives are balanced. You don't really need to evaluate it. The evaluation is simple. But bk is, other than k is equal to 0, is equal to ak times that thing, and let's substitute the formula for ak. It was sine k pi k over 2 divided by pi k e to the minus jk pi over 2 for k different than 0, and it's equal to 0 when k is equal to 0. So B0 is equal to 0. From here now I will continue. This is just a review of what we did last time. The continuation of this example is as follows. Now let's have an even further signal, which is, let's call it z of t. And that is here we have 2, 1, and this is 4, and it repeats. A triangular waveform like this, and the peak value here, they must be equal, sorry about that, is equal to 1. So this is our new sequence. If you try to solve this question using the integral formula of AK, then you will see that you have to use, for example, something like t over 2 here, and minus t over 2 plus 4 for this part, from 0 to 2 and from 2 to 4. And then you have to multiply them with the proper complex exponentials, e to the j k omega 0 t. And when you do that, you will come up with some troubling integrals. Okay? T times e to the j omega t integrated. That's a problem, and those problems must be handled using properties. That's what the properties are for, to solve questions more easily. What you really need to do is you have to associate this signal to some of the signals that we have seen and look how we continue with the examples. This signal is related with y of t in a sense. What is that sense? Y of t is integration to obtain z of t. Let's say it more easily. This thing y of t is the derivative of this z of t. Okay, it's as simple as that, because the slope here is 1 over 2 and the slope here is minus 1 over 2. That's what we have, 1 over 2 and minus 1 over 2, from 0 to 2 and from 2 to 4, and things like that. So that thing is the derivative of y of t, which indicates that z of t is then the integral of y of t. So this is the formula, and using the formula that I was talking about for the integrations, let's solve the question, because then it will be a piece of cake. It will be quite simple. Let's denote that the Fourier series coefficients corresponding to z is equal to ck. So what are ck's? Ck is equal to 1 over jk omega 0, with the same omega 0, by the way, because the period of this one and those ones, they are all the same. It's always 4. 1 over jk omega 0 times bk, for k different than 0, of course. And that is equal to that thing over there, which is bk sine pi k over 2 divided by pi k e to the jk pi over 2, and we have to multiply it by k times omega 0. By the way, this omega 0 is, what was omega 0? The period is 4, therefore omega 0 is pi over 2. This is pi over 2 for our case as well. So this over 2 goes to the numerator, which makes this 2 sine pi k over 2 divided by j times pi times k times pi times k, which is pi k square, I guess. Both pi is squared and k is squared, and the j comes into the picture. Of course, for k different than 0. Sorry? What? Oh yeah, there's a minus in the exponent, yeah. Okay. So this denominator becomes a little bit different, but the structure is more or less the same. So this is a new set of Fourier series coefficients, and you can see that this is the answer, almost 9 points out of 10, as I always say. In order to get 10 points, you have to tell me what C0 is as well. But that's not a difficult thing. What you really need to do is you need to evaluate the DC value here, and the DC value here is still 1 over 2, because for a triangular form up to the level of 1, it occupies half of the area of a full rectangle. Therefore, since this is only half of it, the DC value we claim to be 1 over 2 only. And if you just take the integrals, this is what you will find anyway. All right? So when you also say that C0 is equal to 1 over 2 separately, then the answer is complete and you get 10 points. So this is the answer for CK. For k different than 0, it's this expression, and C0 is equal to this. So you see how we find or solve the questions. It's a good idea. It's a good idea to make the verification, if you wish. Why don't you take the derivative of this thing to get here? All right? Does it really correspond to the same thing? So what you really need to do is you have to multiply by jk omega 0, with omega 0 being pi over 2. Does it really correspond to the same Fourier series coefficients of this one? Of course, we did the opposite. Therefore, the inverse verification is also something valid. So there's no problem about the solution. Yes?
Hocam orada C0 bulurken siz K'ye 0 vereceğiniz zaman denominator bir çarpı K yani. K 0 olduğu zaman onun tanımı zor mu?
Yes.
Nasıl diye oluyor?
That's why we handle C0 separately. Because here when you consider K is equal to 0 case directly from this thing, this expression, it will be a bit more difficult. What you really need to do is you have to apply the hospital's rule again. You have to take this numerator and this denominator and take the derivatives of them with respect to k. Even when it's not enough, further take the derivative, the second derivative. You just continue unless you get some number, and that number happens to be 1 over 2. That's for sure, that is certain, there's no doubt about that, but it's quite doubtful if you do it from here. I don't recommend that. Don't try to get C0 by substituting k is equal to 0 here, because as you see, this is a multiplication. There is a sign and a complex exponential. So when you take the derivative with respect to k, you have to apply the chain rules of multiplicative terms, which is still problematic and not very easy. Highly unrecommended to continue from here. But even if you do that, you will have to find the same solution. So if in an exam, if a student does it that way, I don't want to evaluate C0 separately. This is the answer, and from here I want to show that C0 is indeed 1 over 2. He or she must come up with the solution of 1 over 2. If you do all the algebra and come up with an expression like 1 over 3, for example, then you won't get the 1 point credit as a correct answer. So you should proceed the easy way to get the correct answer. Engineers, unlike other scientists, are expected to come up with correct answers. All right? An incorrect answer is not tolerable for engineering. Of course, for students, they are a little bit tolerable, but you should start learning not to get errors. The continuation of the same example now is, well, it's not the continuation, but I will combine the examples later. The signal that we have to first consider is a different one, that is consisting of impulses. Like this, for example. And the magnitudes are units. So these are unit impulses that we have. An impulse train is what they call a funny name. Okay, an impulse train. And in Turkish, the translation is even more amusing for me. Dürtü katarı. Impulse train. So, it is a periodic sequence. Ironically, it is periodic, but the samples are having infinite values, but the magnitudes are not infinite, they are finite. The magnitude is in terms of the area under the infinitely narrow and infinitely tall impulse. The area underneath is equal to 1. What can we say about the Fourier series coefficients then? Because it doesn't violate any Dirichlet conditions. The Dirichlet conditions, as you may remember, says that the integral within a period, the absolute integral must be finite, and here from minus t over 2 to t over 2, when you integrate, it is equal to 1, so it is finite. And the number of discontinuities must be finite, and there is only one discontinuity here. In fact, technically two discontinuities. One upward going to infinity, one downward going to infinity. So there are two discontinuities. We must have the Fourier series coefficient expression. And in fact, when you evaluate from the formula, it's very easy to come up with a reasonable expression of AK. Into here we must write x of t within this period from minus t over 2 to t over 2. So what is the expression of x of t within there? That is delta t, right? By the way, the expression of this thing is equal to k from minus infinity to infinity delta t minus k times capital T. That is the impulse train consisting of infinitely many impulses from minus infinity to infinity in time. But within one period, it is only delta t. And then e to the minus jk omega 0 t. Let me substitute this omega 0 already. 2 pi over capital T t dt. Well, it doesn't really matter if you just write omega 0. This is just an alternative. Now, what's happening here is that this delta t is non-zero only at t is equal to 0. We know it, right? For all other t values, we don't even have a delta t. What happens then? This is a very narrow signal, and this is a signal valid from this range to up to this range. So, but it's a complex signal. But anyway, let's assume that it is something like this, which is not. And we are multiplying it by delta t. This multiplication output is the same as this delta t multiplied by this value only. And all the other places inside the multiplication term are zeros. What I say is this. This is delta t, and over here at the right hand side we don't even have a signal. We only need this value here, because only at that value this impulse is multiplied, and that corresponds to t is equal to 0. When t is equal to 0, e to the 0 is 1. So that's it, we are finished. And that thing, this integral, clearly corresponds to the area under the impulse, which is by definition something known. We know it. It is 1. So the answer is 1 over t. Let's read it from here. AK is equal to 1 over t. Good, right? Fair enough. But it is a little bit different than what we expect, because it doesn't depend on k. There is no k term. Do you remember in the rectangular case, as we have done in the previous example, it was 1 over 2, 1 over pi k, 1 over 3 pi k, 1 over 5 pi k. So the k was in the denominator and it was all decaying. Over here it's all the same and it's never decaying. And this is the only type of signal, an impulse train, and combinations of impulse trains are the only types of signals whose Fourier series coefficients do not decay. They stay constant. That constant staying means that such a signal has harmonics at every frequency at the same amount. From physics, do you know any such signal having the same harmonic from every frequency? Or let's change the frequency concept to a more physically known concept, wavelength. I'm already hinting about this answer. That is the white light. You remember that? A white light, those lights, not these ones, they're not very white, but the sunlight, let's say, contains harmonics at every wavelength, which means they have harmonics at every frequency, light frequency. And that corresponds to a white signal. So this thing has equal harmonics at every frequency. It is a very high frequency signal then, because all the others at abrupt changes, they correspond to some very high frequencies, but they are not as high frequency as an impulse. An impulse is altering the signal from 0 to infinity and back from infinity to 0, which makes the highest possible frequency in continuous time. So these are the highest possible frequency signals in continuous time, and their harmonic magnitude never decays even at the highest frequency of infinity. It's always 1 over t at all harmonics. So that's an interesting signal. Now, fortunately, we're not interested in the physical meaning or what sort of a signal it may correspond to. We are interested in solving questions more than that. Let's consider this signal at the bottom. I'm erasing this one. But I'm keeping this signal. Because guess what? I'm going to take the derivative of that signal and call it, I'm going to call it y of t. The derivative of this signal. The way to obtain an impulse as a derivative of a signal is the utilization of these step functions. When you take the derivative of a step function, you get an impulse. If the step height is equal to 1, the derivative corresponds to a unit impulse. If this height is 1 over 2, for example, then what you get is 1 over 2 times delta t, or the corresponding placement of an impulse. If it is negative like this, then what you get is a minus delta t if the magnitude is 1. If the magnitude is minus 1/2, then you will get minus 1 over 2 times delta t, for example. So the derivative of this signal can be drawn as something like this. And it's extending. Look at the time and you will notice that it is periodic, and it indeed corresponds to the derivative of y of t, x of t, sorry, the time derivative of x of t. Now, a good way to verify all these formulations and all the integral derivative formulations is to obtain the Fourier series coefficients of this top signal y of t from the derivative of x of t, which is just as simple as multiplying by jk omega 0, and from the previous example of impulse train as well. Are they the same? Can you find, or can we find the same thing? That would be a very inspiring exercise. First, let's try to write y of t in terms of the impulse train. We didn't give a name to this impulse train in the previous example yet. We should better give a name to that, but we are running out of names. What kind of a name can we think of? Give me a letter. Lambda. Good. Okay, that's lambda of t then, the impulse train. In terms of the lambda expression, by the way, this is 1, this is 2, and this is 3, this is 4, and this is 5. Let's assume that this t is equal to the same with or compatible with that one. It's equal to 4. That is, the top, the upward going, or the positive magnitudes are separated by 4, as you see. So these are periodic with 4, and the downward going arrows are also periodic with 4. Then I can write y of t in terms of lambda of t like this. It's equal to lambda of t plus 1, which is the shifted version of the impulse train to the left by 1. And minus, yeah, because they are negative, the others are lambda of t minus 1. The others are shifted to the right and pointing downwards. Now, what does this make in terms of the Fourier series coefficients? It corresponds to, or the Fourier series coefficients of y of t, let's call them again bk, is equal to the Fourier series coefficients of this one minus the Fourier series coefficients of this one, because of linearity property. When we combine these two, then we will have the Fourier series coefficients. So when you shift, what was the formula? E to the j k omega 0 is pi over 2, and t0 is 1 with a minus sign. It is, when you say t minus t0, that t0 is already minus 1, so this minus sign and that minus 1 is cancelled, and we get a positive value times the Fourier series coefficient of lambda t. What was that? It was 1 over capital T, which is 1 over 4 for this example. Capital T is 4. Okay. Minus e to the, this one corresponds to minus jk pi over 2 times 1 over 4. Now, can we make sense of this one, or can we combine these things? It's not really cosine because there is a minus sign in between. Therefore, it must be a sine. But in order to have a sine, we have to multiply it by 2 over 2 times j over j, and this j will remain at the top, and let's put this over j here. This multiplication, this denominator will stay wherever it is, but this top will be inserted to here, so it will be 2 over 4j, and 2 over 4j's will become 1 over 2j. And therefore finally we multiply it by j over 2 then. And now this is plain sinusoid, and that sine signal is equal to j over 2 times sine k pi over 2. Now it's interesting, this one is truly interesting because it depends on k, but it doesn't decay, it doesn't go down, because it's a sinusoid, and inside a sinusoid, for a value of 0, for example, it gives you a 0. For a value of k is equal to 1, it will give you 1. When it is equal to 2, it will give you 0. For 3, it will give you minus 1. And then 0. And then 1, 0, minus 1, 0. 1, 0, minus 1, 0. With a scaling factor of j over 2, whose magnitude is equal to 1 over 2. So, we see that this is not decaying. It is oscillating. Plus 1, minus 1, plus 1, minus 1, and in between there are zeros. That is also an interesting Fourier series coefficient pattern. It's a bit strange. It's not decaying. K is inside the sinusoid, so the value is oscillating. Now, even more interesting than that is the attempt, which I will start, but I will not continue. The attempt to have this y of t as a derivative of this thing, because we also know that y of t is equal to the derivative of x of t, and the Fourier series coefficients, do we really get this one? And the answer is yes, it must be yes. So it's a nice test of your algebraic skills, whether you come up with the correct combinations and simplifications. So from here, what we simply say is that bk is equal to j times k times omega 0, which is pi over 2, times the Fourier series coefficients of x. What were the Fourier series coefficients of x? It was sine pi k over 2 divided by pi k already. Well, we are there. You don't even need to make any simplifications because these k times pi and these k times pi are cancelling each other, and we immediately come up with j over 2 times sine pi k over 2, which is the same. Okay, so it's up to you. It's your choice to attack the problem and solve the question's requirements using the properties, in fact, that we have all seen. You may use this property and start from lambda and come up with this expression, or you may take the derivative of x of t, whichever is easier. They are equally easy, technically, but one thing you have to make sure is that unless you are stuck, you should never consult to that integral formula for determination of the Fourier series coefficient. It is, of course, possible to find the answer, for example, from 0 to 4, you take the integral of x of t times e to the minus jk omega 0 t. And since this is an impulse and this is another impulse, the integration will appear only at 2 points, and that integral will have to give you this same thing. But it will take longer. And if these are not impulses and other things, but other things, then it may be even more difficult. So don't solve the questions like that. Okay, don't try to find AK from the integral. Always keep it in your hands, a copy of those properties, and try to associate your signal with something that you already know. The association may be a derivative integral formulation like this, or it may be in terms of shifted and linearly combined version of some other signal like this, for example. The rectangle thing, this thing, has a known Fourier series representation. This thing has a known Fourier series representation. A cosine or a sine has a known Fourier series representation of two coefficients only then. So these are the known typical pairs. So how do we solve questions then? You have typical Fourier pairs. By saying pair, I mean x of t associated with ak for some certain things. And then you also have properties. These two are the things that you need mostly for solving normal questions. You look at your question, associate it in terms of the properties with a known Fourier pair like this, and then attack your problem. All right. Now I will write down a question, and then I will stop. We're not going to solve it. But this question, or such questions that we have, I'll try to explain where we encounter such questions first. Because when I write the question, you will have the impression that it looks like a torture. I mean, why are we solving such questions? It's quite artificially fabricated, you will say. The question is as follows. For a signal, for a periodic signal, we know these things. X of t, that is the signal, is real. That is a side knowledge. And the period is equal to 4, and the Fourier series coefficients are AKs, which we don't know, and we're looking for that. As another knowledge, we know that AK is equal to 0 for k greater than 1. So A2 is equal to 0, A minus 2 is equal to 0, which reduces our signal to only three Fourier series coefficients, A minus 1, A0, and A1. And we have an auxiliary signal y of t has Fourier series coefficients bk's associated to the original signal's Fourier series coefficients as this, e to the minus j pi k over 2 times a minus k. Now what does that mean? It means that y is a shifted, an inverted, time inverted, because bk is equal to minus a minus k from there, and shifted version of x. So we are unable to observe x, but we are able to observe a y of t, which is reflected and shifted for some reason. And we don't really observe y of t, but we say that y of t is an odd signal. We observe it to be an odd signal, not an even signal. And finally, we see that the average power of this signal is equal to 1 over 2. So that is the average power. We are not observing the signal, we are observing its average power. We are not observing the signal, but we are looking at a reflected version of it, reflected and shifted version of it. We know that it has only three harmonics, A minus 1, A0, and A1. and the period is 4, and it is real. So these are the things that we know for a signal. The question is, what is x? Can you write an expression for x as accurate as possible? Now, where do we encounter such questions is the thing that I will mention about, and we are going to solve it next week. We encounter such questions here. In signal we require signal processing in several places that you may not even imagine. Geophysics, for example, or astronomy, and things like that. In such cases, you have observations, but you don't have the signal. Even a simple digital camera, when you acquire a picture, take a picture, the output that you have, which is a file of a digital image, it is a signal, but the acquisition process is getting something else. It is getting some voltages, some observations. We are not observing the pixels. We are observing voltages. From those voltages, you have to make some processing to come up with the value of that pixel of interest. Let me give it in another example. Did any of you ever have a computed tomography scan, CT? Did you ever have a CT tomography? Luckily, no. Okay, that's good. But maybe you already know what a CT corresponds to. It corresponds to the imaging, radiological imaging, of a portion of a body. But unlike the X-ray, which is from here reflected to the back, and you take a look at the picture, it's not like that. It is a slice of your body. A CT, a tomography, gives you the picture of a slice of your body. How can you take a person's slice image, the image of a slice? Are you going to cut that person and look at what's inside over there? No. So how can you do that? How can you do that? Doing that requires processing from several side informations. You take X-rays from several directions. That's why a rotary machine is over there taking images from every angle. And from every angle like that, it reconstructs what could be inside your body as a slice, in your brain, in your abdomen, or whatever. Okay? That's how you acquire. And such a problem is quite reasonable. For example, in the satellite imagery of, what was the name of the telescope sent to the outer space? Hubble, yeah. Hubble was malfunctioning. Okay, it was erroneous. The lens was erroneous. They cannot fix the lens because in order to fix it, you have to send somebody over there to fix it. It's impossible. But they fixed it. How did they do that? They fixed it at home. Because there are some signals coming. A telescope never acquires an image of a deep space. Okay? You don't have it. It gives you some signals. From those signals, it is the engineer who needs to show the stars and make an image out of it. So it's not always the case that you observe your signal. You observe some information instead of that, like these. You have these informations, you observe them, and from these you reconstruct your X of t and give it to your boss. That's what a signal processing engineer is supposed to do. You have to give me the signal, which you don't have. You only have information regarding the signals. So this is a very commonly encountered situation. Life is not as easy as getting the signal from the tool. The tool is doing something. The tool is observing something, and from there it says that X of t is this. Okay, so this is a reasonable question. That's what it is. And knowing that this is a reasonable question is as valuable as the answer to this question. Okay, which we will do next week. We can stop now. Yeah, the quiz. We are a bit out of schedule. We are late anyway, so we didn't have the time to make a quiz for today. Starting next week, we will continue. Today, all right. Let's fill an attendance and give it to Shukru, so that the other guys who did not come will not benefit from this. Yeah. No, yeah, this paper is enough. No.